Today we are going to talk about an important aspect of design, that is reusability of design. How much of our old designs can we reuse in our new context? A few years ago, researchers in object-oriented software engineering realized that there are many commonly occurring patterns which repeat again and again in different domains. Even if the requirements are different, the class level designs, if you see, there is a lot of similarity. So they thought, why not look at them carefully, document them as reusable patterns. So we are going to talk about these patterns called as design patterns. They are patterns of design. They are called patterns because they repeat again and again. A pattern is something that repeats again and again. Then we say that it's a pattern. So this lecture is about design patterns. So if we look at reuse in software engineering in general, we can see that reuse at code level is very common in software development. In this slide, we can see that reuse in software engineering can be obtained at various levels. The most commonly occurring reuse is at code level. We reuse code. For example, C standard libraries such as mat.h, stdio.h, GUIs in Java, or even the user-defined libraries such as bank.h, library.h. You're developing banking software or library software, you might design some of those classes and implement them as readily available implementations and use them in your code. So these libraries, these .h libraries in C, you know that they provide the prototype definitions, and the actual code or the implementations of these prototypes are available in their corresponding .c implementations. So the .h files that you include in your code represent the reusable code. So these are typically shipped by the designers of the software. Along with the language, you get these files bundled with the language environment. So this is an example of reuse of code. So what about reusing old design solutions and not just the code? That is a question. We should be able to reuse the design solutions and not just the code. So for example, we have designed a class diagram, a typical way of interaction among the classes. Can we use those results? That's where now we talk about patterns in software engineering, or specifically patterns in design. So studies in other disciplines are very helpful in software engineering, apart from computer science, which is its basic discipline. The research in design patterns was motivated after patterns in other disciplines such as architectural patterns. If you look at building architecture, you see patterns everywhere. Sitting spaces, for example, you look at a 3-bedroom, 2-bedroom, 1-bedroom house, kitchen with whatever kitchen and your basic sitting spaces, the hall. When you enter the house, where do you enter? So these are all patterns. If you look at temple architectures, there are patterns. There are different kinds of architectures. So there are patterns belonging to every kind of architecture. So you see the patterns in real life in different disciplines, and software engineering researchers also thought that one can have these patterns in software design. So object-oriented software engineering has benefited from object orientation, which enables us to represent these patterns as collections of classes and interactions amongst them. So what are design patterns? These are solutions to commonly occurring design problems, object-oriented designs, and not code in specific programming languages. These are designs and not code. So we are not talking about just the reusable code as in libraries which you use through .h files, or in Java you import existing classes, you use them as it is. We are talking about designs. So typically, if you look at design patterns, they involve a few classes, maybe 3, 4, sometimes even 2 classes. So we are talking about collaborating classes. Now if you have a design of such collaborating classes, you should be able to use that design in a different domain. Now how do you represent these patterns? They are represented abstractly. You identify roles with every class and then explain them with concrete examples. And then this abstract design is mapped to a concrete problem. So you can imagine a set of design patterns. Say you have a pattern library in which all these abstract designs are documented, and when you document them, certain template has to be followed. Now when you look at these abstract designs, each class is given a role and it has a specific set of member functions which are defined very generically, so that you can map them to concrete problems which are different, and in the concrete problem you have different class names, different function names. These are all very specific to the problem, whereas in the design pattern description you don't have to document the exact names and the exact specifications of a given problem, but it's necessary to document them very generically, and then it can be assisted with the help of an example. There are various kinds of design patterns. For example, there are creational patterns, structural patterns, and behavioral patterns. Now how do you describe a design pattern? First you specify the generic problem that is to be solved, motivate the design pattern solution with the help of an example, provide the structure for the pattern, discuss collaborations between classes, and discuss other issues related to the pattern such as the trade-offs, implementation techniques, etc. So these are the things which we just listed. The generic problem, what is the generic problem that you want to solve? So that if a designer has a specific requirement, he can just go through this list of existing patterns and see whether his requirement matches with any of these generic problems specified by the pattern, and then he looks at the example and sees whether the example is also similar to what he has in mind. If that is the case, then he can go through the structure and then implement it in his domain. So the specific template followed by Eric Gama and the team who wrote the famous book on design patterns is as follows. We first specify the name of the pattern. So every pattern is given a name. So there are many patterns which are described by Eric Gama and other researchers. There are pattern descriptions given by many researchers. There are a few books available. I will be giving the references at the end of this lecture. So you first start with the pattern name, then classify the pattern. What kind of pattern is it? Is it a creational pattern, or is it a structural pattern, or is it a behavioral pattern? So what is the focus of this pattern? Patterns can also be classified according to the technological domains. For example, is this pattern meant for distributed systems? Is this pattern meant for real-time systems? What kind of pattern is this? So we are talking about design patterns today, but there are patterns in other for other life cycle phases also. For example, there are coding patterns, there are analysis patterns, and so on. So one has to classify the given pattern. then what is the intent of it? That means what is the kind of problem, generic problem that it wants, that it solves, and then give the motivation for the pattern. Talk about its applicability, where it is applicable, then give its structure, participants, collaborations. Participants are all the classes in the, they are all classes in that particular pattern, and then how do they collaborate with each other, what is the protocol, and then various aspects, various other important aspects about the pattern are also discussed. For example, what are the consequences of using this pattern, are there any limitations, what kind of implementation it needs. If you look at implementations of patterns, they could be different in different programming languages. The same pattern can be implemented differently in, say, C, C++ and Java, object-oriented language, C++ and Java. They can, or Smalltalk. If you implement the same pattern, the implementations will look slightly different from each other, because every language has different constructs, or they vary from each other. For example, multiple inheritance of classes, concrete classes, is not supported in Java, whereas it's supported in C++. So the implementations vary a bit. And then you have to also talk about the known uses of the pattern. Something becomes a pattern only if it has been used in different domains. There must be multiple uses of it, otherwise how can it be a pattern? You may have a very specific solution in your application domain, or in your specific application. You can't call it a pattern unless you establish its reusability, you show its existing known uses. And then you have to also talk about the related patterns. What are the different related patterns, so that one is able to distinguish among the closely related patterns and apply or use this specific pattern to should be able to choose it rightly. So we have just seen that there are creational patterns, there are structural patterns, there are behavioral patterns. Creational patterns are concerned about the ways to create new objects. How do you create new objects? Structural patterns are concerned about the composition of objects and classes. How objects are connected together, what kind of composition is this? So the main focus is on the structure. And behavioral patterns are concerned about ways in which the objects interact. How do they interact? Is the message sent from one object to another, and from that object to another object, and so on in a sequence? Or is it a broadcast kind of message, or is there a handshake protocol? So there has to be a structure if the objects have to collaborate. But in behavioral patterns, the behavior or the collaborations are more important. They are in focus. Similarly, in structural patterns, there will be collaboration, but the structure is more important. And in creational patterns, what is more important is the way you create objects, how you create. You know, the simplest way to create is simply use the class and instantiate the class. But then there are other ways to create objects, and we will see some examples subsequently. So these are the examples of creational patterns. There is a pattern called singleton pattern. It talks about creating a unique instance of a class, a sole instance of a class. That means, firstly, the class should be able to create an instance, and secondly, it should be able to create only the sole instance. If it has created the instance earlier, any other request should give you only the old instance. One should not be able to create more than one instance of that class. Then you have another pattern called prototype. Prototype pattern gives us a solution for object creation from a given object. How do you create a new object from a given object? I have an object handle with me, but I don't know what is the class of that object, and then how do I create an object similar to an existing object that I have? Prototype pattern gives us the solution to that problem. Builder pattern creates an object from an existing representation. there is something existing from which you have to create an object. Factory method refers instantiation to subclasses so that you can have polymorphism on creational methods. An abstract factory provides interface to create families of objects without specifying the concrete classes of the object. So these are various kinds of creational patterns. We are only going to go through one or two examples in this lecture. Then there are various kinds of structural patterns. Some examples are mentioned on the slide. Adapter pattern, it converts an interface to another. So you know the AC to DC adapters which you use very regularly. So there are adapters in software engineering too, in your software too. It converts one interface to another. Composite, it composes objects in a tree structure. So you have tree structured objects and you want to represent a design for such trees, so that you should be able to create an arbitrary tree satisfying given properties. Then we talk about composition or composite pattern. Decorator pattern allows you to attach additional responsibilities dynamically. A facade pattern provides a unified interface to a set of interfaces in a subsystem. Bridge pattern decouples abstraction from implementation, and it lets them vary independently. Abstractions can vary independently, and implementations can vary independently. So these are some examples of structural patterns. We will again see one or two patterns in this lecture, and then these are some examples of behavioral patterns. For example, template method. It lets certain steps in a superclass be defined by the subclass. Look at the keyword steps here. So you may have a member function implementation in the superclass, and some calls in that member function implementation, or some function calls in that member function implementation in the superclass may not be concretely implemented in superclass itself. They have to be provided by the subclasses. Now such a method that is implemented in the superclass in terms of non-implemented methods which need to be implemented by the subclasses is called a template method. We are going to see an example of template method later. Strategy pattern encapsulates a family of algorithms and makes them interchangeable. You can apply different strategies at different times. Iterator pattern provides accessors for iterating over the elements of an aggregation. You have a collection. Now you want to take a specific action for all elements in that collection. You have to go over the collection. Now in order to do that, what is the solution? How are you going to iterate over a given collection? The iterator pattern gives us a solution for that. Observer pattern allows us to design the observers or the producer consumers kind of network, or the event generators and action listeners kind of collaboration. If one object changes the state, it lets its dependents be notified automatically. Observer keeps track of the observed. And there is another pattern called state. It allows an object to alter its behavior when it changes its state. So these are some examples of behavioral patterns. We are going to look at some of them in this lecture. Now let's start with some concrete patterns. So the first one, let's start with the problem. So read this statement. In a graphical editor, by clicking on an object, one can obtain a copy of the original object. Obtaining a copy of an existing object is a common design problem in online composition. We can provide a design solution to solve this problem and reuse this design whenever similar solution or similar situation arises. So all of you must have used one or the other graphical editor. You know that you can click on an object, a part of the figure, and by say right click, you get a menu there and you can make a copy of it, and then you can use that copy. So you have drawn say a rectangle, you want another copy of the rectangle, you can simply click on it and then you get a copy. Now you can apply this kind of technique to any shape on your drawing board. You can apply the same click and copy mechanism to lines, to squares, to all shapes that you have drawn. That means the graphical editor is able to treat all these shapes as clonable ones. Now whenever in whichever application you have this requirement that I have identified the object and I want a copy of it from the object, the user is not going to specify the class of that object. The user just identifies the object and he can obtain a copy of that object. So whenever this requirement comes, the solution that you have adopted in the graphical editor can also be used in that specific domain. Now let's look at this solution. So on this slide we see that you have organized your objects, your shape objects in hierarchy. So you have the superclass over here which is titled as shape prototype. It's a prototype for all shapes and it supports a function called clone, member function called clone, and you have a circle prototype and you have a rectangle prototype. So this is actually your circle class and this is your rectangle class. They have to implement this method clone, and this is your client code. The client code is that part of your application which accesses all shapes and asks for clones of the selected shapes. So the client has this link into this hierarchy. Now through this link and through this polymorphism you can point to any of these instances of the subclasses and ask for a clone of it. The client code does not need to be aware of what is the exact type of the object, whether it's a rectangle or whether it's a class, when it's asking for a clone. So what happens here is that when you click on the mouse, the object handle is returned to you, and on that object handle you simply invoke this clone operation, and the clone operation gives you in return a clone of the object that you have selected. The creation of the clone is done by the object itself, the object which you have selected, but the client code or the application code that is asking for a clone is not aware of the type of the object that the mouse click has selected. The mouse click just gives you a handle to the object that was selected by the mouse click, and then once you have the handle to the object, that handle is of type shape prototype. So treat it as an instance of type shape prototype, but the actual instance is from the subclasses. So this is a solution that is adopted by our shape hierarchy or in our graphical editor, and these small boxes show the implementation. How is the clone implemented? You copy the cell. So this is pseudocode. You have to, when you are copying the object, you know the concrete type, you will create an instance of this rectangle prototype and you will copy the entire state of this rectangle into the cloned object and then return the cloned object. If you have sub objects in this object, you have to copy them all. So it could be a deep copy if needed. Now this is a specific solution in our graphical editor, and the classes are named as shape prototype, circle prototype, rectangle prototype. But where is the pattern? This is a concrete solution in a given application. Where is the pattern? How do we document the pattern? How do we represent the pattern so that it can be also applied in a different domain? So here is the pattern description. If you look at this, now the shapes are gone from here and what remains is the prototypes. So you have a superclass called prototype, and you have concrete prototype 1, concrete prototype 2 is a client, and there is an operation. In the operation, you are calling the clone on the prototype, and the clone operations are implemented as copying, by copying of the self. So this is your pattern, and then it can be described in abstractions using these abstract names. Now any application that has a similar need can identify its own concrete superclasses and subclasses and map them onto this prototype hierarchy. So we can apply this prototype pattern in a different domain. Now we are going to look at another creational pattern called singleton pattern. Singleton is a class that creates only one instance at most. Even if you try to create another instance, it should always give you a copy of the instance that it has already created. For example, in this diagram, the class is named as singleton. Now one question should come to your mind, that if you just use the creational methods provided by your chosen programming language, will you not be able to create many instances of a given class even if you want to make it as a singleton? Say, take for example class stack. You can just say stack s1, s2, s3, s4, and you have got 4 stacks in C++. Or you can say stack s1 equal to new stack, stack s2 equal to new stack, and so on. Say in Java, and you got 4 stacks. Now how are you going to prohibit this creation, this kind of creation which the programming language itself provides you? Now the solution here is that if you put your constructor in your private compartment, you first prohibit this kind of creation provided by the language, and then support a specific method which is called as class method and not an instance method. Class methods are represented by keyword static in C++ and Java. So you can see here that you have a get sole instance method, that is class method. It's a static method, so you have to call it on class. You may have to use an operator, a different operator, to call a method on the class directly. When you are getting an instance, there is no other instance available. You are getting your first instance, there is no other instance available. You have to invoke this method on the class. So this is a static method, and you invoke it on the class, and the get sole instance method returns you with the sole instance, which is also a class variable. So you can see that it's named as static sole instance, and the data and the operation belong to the instance. They are not static. So this is your singleton pattern. So the implementation that we just discussed makes use of this facility of compartmentalization of private and public members, that is hiding your constructor using by describing it as a private member. It prohibits the normal creation mode, and then a new instance can only be created through a class method, which are described as static methods, and the class method then can be called by an environment to get the instance. And if you call it again and again, the method can be programmed to check whether already an instance has been created or not. The instance is also a class variable. If the instance already is available, then it returns the same instance. There is a unique instance for this class. And here is the pseudocode for a typical singleton class. So you have singleton, that is a constructor in this class singleton, which is protected. Protected is it's protected because your subclass is also should be able to benefit from this pattern. And then you have your static method called sole instance, and you have your singleton, which is also sole instance. The get sole instance method gives you this instance, and the sole instance handle points to this sole instance. Okay, now we looked at two creational patterns. First one was prototype, second one was singleton pattern. Prototype allowed you to create objects from a given object. Singleton pattern allowed you to create a unique instance of a given class. So if you look at these requirements, these are very generic, they can occur in any application. And now you know how to go about designing for these requirements, against these requirements. And then the design are also documented in terms of abstract names, the classes and collaborations among them, and the structure amongst them. And then you also have some concrete examples documented along with the pattern. And now when you go through a given pattern dictionary, if you match the requirements with the intents provided along with the pattern description, you can select a specific pattern and apply it in your application. Now we are going to look at some examples of structural patterns. Let's look at the adapter pattern. Now adapter is something like you are say converting an AC to DC, AC voltage to DC voltage. So this is an example from software domain. You are building a collection class hierarchy for collections such as FIFO, set, LIFO, etc. FIFO is first in first out collection. Set gives you set semantics. LIFO is last in first out collection. And now, so this is a collection hierarchy. You may have an abstract class called collection, and then all these are subclasses which you need to implement. Now you find that there is already an existing class called stack, which can be used for providing the LIFO collection. So how do you adopt the existing class stack to the new interface of the collection classes? This slide shows our solution. Firstly, look at the collection class hierarchy. So you have this collection superclass which specifies two member functions called insert and fetch. You should be able to insert an item into the collection and fetch an item from the collection, out of the collection. Now you want to build a LIFO type of collection and a FIFO type of collection, and these specific collections or these concrete collections are going to implement the abstract member functions declared in the superclass called collection. Now when you are implementing LIFO, you want to use the existing class stack, but you see that it has a different interface. On stack you are calling it as push and pop. Now you want to map it to insert and fetch. How do you achieve this? So you are trying to now look at the intent of this pattern. We had described it earlier. You are adapting this interface push pop to insert and fetch, because the client application here is going to use this object hierarchy through this specific interface only, that is insert and fetch. The client knows collections, that is of type collection. It may be either FIFO or LIFO, and the client application can simply call insert and fetch. But now since we already have something called stack with another with interface called push and pop, why can't we simply map push and pop onto insert and fetch? That means that is to adapt one interface to another. So the solution is adapter. Now you must have figured out by this time how we should be able to do that. So in your LIFO class you have insert and fetch. Now for example, fetch implementation has been given, you simply call pop. Now you use multiple inheritance here. LIFO inherits from this abstract class collection and the concrete class tag and implements insert as simply by a call to push and fetch by a call to pop. Now if you use inheritance, you can simply make these calls as if the functions are available onto you locally. So the pattern can be described as follows. On the earlier slide, we had the concrete solution for an example, that was collection hierarchy. Now here you replace your class collection by a more abstract name called target. So this is a target, this is your adaptee, and this is your adapter. The adapter is a subclass. The adapter adapts the adaptee to the target. The client uses the target. The client knows only the target's interface, that is request. Adaptee has a different interface called specific request, and request can be implemented as a call to specific request if you use multiple inheritance here. So this is called class adapter. You are adapting a given class to another class. So it's at class level, and you can also have a slightly different solution called object adapter. If you do not want to use multiple inheritance, or if you want to change the objects to be adapted dynamically, you could go for object adapter. So instead of going for multiple inheritance, you use an instance directly. Now you can see that the request is implemented as adaptee arrow specific request. That means you are going to make a call on a given object. You could use this object as a part in the adapter. You could use an instance of the adaptee as a part in the adapter. So this is another solution, or this is a different solution called object adapter. You can use object adapters if you do not want to use multiple inheritance. For example, in this hierarchy, if the target is partially implemented, then if you are using a language such as Java, if you have this as a full class, you won't be able to use class adapter, because then you have two concrete classes. Then you will have to go for a slightly different solution, which is your object adapter. Or if you want to change the objects dynamically, then you can't go for class level adaptation, because if you go for class level adaptation, then you are stuck with one instance only, which directly comes as a part in the subclass. Now you can go for object level adaptation. So these are two solutions to adaptation. So this is your adapter pattern, and these are the descriptions of the pattern. So we saw that in this slide, this is a concrete example on class collection, whereas later we can describe the same pattern using abstract terms. So we have a pattern now. Whenever this adaptation requirement comes to us, we can use this solution. Now we'll go for another structural pattern called composite pattern. Now this is an example. A graphic document is composed of graphical objects such as lines, rectangles, circles, text, images, or other graphical documents. Now if there is a graphical document inside a graphical document, or say a picture in a picture, and a picture can also have shapes inside it. A picture can be composed of lines, squares, rectangles, and so on, or a picture can also contain pictures. Now those pictures can also contain pictures and so on. So if you want to represent a design for this, you could draw different object diagrams. Say for example, in one object diagram you could have one picture at the root level, and then it could have some leaf shapes directly and some 2-3 pictures in it. Now those pictures can also have some leaf shapes and 1 or 2 pictures in them, and finally you will have leaf shapes at the bottom of the tree. So you could construct such trees, but then what should be the design? The design has to be closed. It must have finite number of classes. You can't show it as a running tree. So what is going to be your design for this particular requirement? So here is the solution. So you represent this as a composite. Now you can see that there are two interesting links amongst classes. One is inheritance and another is aggregation. or we'll call it composition. In UML, there is a slight difference between these two concepts, but now we will use them interchangeably. More generally, you can call it part-whole relation. So there is inheritance and there is also part-whole relation. So you have graphical element as an abstract class, abstract superclass here, which has functions like draw, and there is also a function called add, and then you have circles, lines, and graphical documents. So you have various functions on graphical elements, and you have different subclasses which implement graphical element. Now in this graphic doc is a composite, which is represented by this link. So you have this part-whole relation. So a graphical document can contain many graphical elements, and through inheritance those graphical elements can be either circles, lines, or graphic docs. So this is how you can represent the design of your tree structured graphical document. So these are your leaves or leaf level classes, and these are the intermediate graphical documents, which are compositions, and the client handles all of them as graphical elements. If you delete a graphical element, if it's a graphical document, it should pass on this delete to all its components. For example, this draw, if you want to redraw or if you want to draw a given graphical element, if it happens to be a composite graphical element or a graphical doc, then the draw is implemented as for all G in these G's in this link, on this part-whole link called draw, its parts. Now if the parts are leaves, these draws will be called, and if the parts are composites, these draws will be called, and they will be further propagated into the hierarchy. So for example, this is one object diagram which you can construct after instantiating this given hierarchy. So you have this picture, well, my picture at the root level, it has this hash picture is another picture. Now it has a line and a rectangle, and my picture is composed of hash picture, there is one more picture inside it, a square and a text. So this tree can be generated out of the design that we have just seen. So we have got a pattern called composite, which allows us to represent such tree structured object diagrams through class designs, through designs expressed in terms of classes. So here is our composite pattern. You have a component here, then you have composite, and you have leaves, a leaf. You could have many such leaves. A composite is also a component, but a composite has its parts which are also components. Now through this relation, this part-whole relation, the composites can contain the leaves as well as the composites. Now this is how you are able to represent this tree structure through a design in terms of classes and relations. So two relations are important, inheritance and part-whole. Now we will look at another structural pattern that is called facade. It provides a unified interface for a subsystem. Now look at this picture. This white box is a subsystem which has many classes, and these classes are interconnected, they collaborate, and these outer green boxes are outside classes which are outside this subsystem described by the white box. Now all of them are interacting with this subsystem through one class. Now this class is an interface to the entire subsystem. This class is called facade. Now compare this solution with this solution. You have rejected it because the external classes are interacting with the subsystem directly through different classes in the subsystem. For example, this component is interacting with this class, this component is interacting with these two classes, and so on. Now if there is any change here, you do not know, it will be very hard to reflect the change in entire system. There are too many dependencies. Separation of concerns is violated. The subsystem must be nicely encapsulated behind the subsystem interface, which is called facade. So this is one structuring pattern. You should structure your subsystem in this way. Now we will look at another pattern, structural pattern called proxy pattern. It's a mechanism for communication. Now when you imagine a distributed system scenario in which an object on one machine wants to interact with an object on another machine, can we make the distribution transparent? Can the object that wants to make a call on the remote object be made unaware of this kind of distribution and networking? So if this local object can have an interface, a local interface to the remote object, it will simply invoke member functions on the local interface, and it will not be even aware that this local interface, the implementation of the local interface, is contacting the remote object over the network. So the two aspects, distribution transparency, client is unaware of the distributed nature of the server. In the sense the server is on a different system and the client is on a different system, on a different machine. Location transparency, client is unaware of the location where it is. Firstly, that it is different, it is separately located in a distributed system, and secondly, you don't even need to know where it is located. The client invokes a method on an object as if it is its local object, and that local object which represents the remote object in a local environment is called proxy. So proxy handles provide a mechanism to implement this communication paradigm. This is a solution. So you have, for example, you have an account object which is a remote object, and you want to make a transaction on the account object. Now the client program can be given an instance of this account proxy which implements the interface provided by the account object, that is deposit. The implementation is given in this small box. You are calling deposit on the remote actual object, remote account. So this is the real account which also implements the account interface, that is deposit. An account proxy has a link to the remote account. Now this could be over the network. So the client does not distinguish, or client is unable to distinguish between the real and the proxy because both of them look the same. Both of them follow the super class which is common. The real account implements it actually, the actual deposit will be implemented here, balance will be maintained in the real account. The proxy simply sends the calls to remote object and the results are returned to the client. So this is an interesting solution for a distributed scenario in a distributed object system, which is called proxy. The proxy pattern is represented as shown in this slide. So you have a subject and you have a real subject and the proxy. The real subject actually implements the subject and the proxy simply routes the calls to the real subject. Now we will look at another structural pattern called decorator. So look at this object diagram. A client is making a call and the call is going through different objects and finally reaching its server. This is a text view. The text view has a scroll decorator and a border decorator. So you have different kinds of borders on a view. Now you want to change the borders, you want to add different kinds of decorators on the text view. You should be able to add these decorators. So on a given object, you are supporting a member function. When you invoke a member function on that object, you want to invoke something else, you want to do something else or something extra in addition to what the object provides. For example, you have a shape and you want to draw borders on the shape, change those borders, or you want say in this case you have a text view, and the additional functionality that you want to support is drawing different borders or scroll bars and so on. So can this be done without the client knowing about what you are going to add in between and how many such decorators are you going to add? Now we are calling it decorator because the pattern suits very well in for user interfaces, but the same requirement can also occur in a different application where you want to add something new on top of what is existing, and you want the client not to be aware of these internal additions. So this is your hierarchy. So we are not going to go through all the details of this particular structure, but you can study the structure and the implementations through the reference books that I am going to cite at the end of this lecture. But what you can notice is that you have this decorator. So again you have two kinds of relations. So you have this one link to the superclass, and you also have the inheritance. So you can see that there are different kinds of decorators, and the decorators has a link to the actual component, and the decorator and the actual component or the text view exactly support the same interface, so that the client is not aware of what about the exact type of the object, whether it's talking to the actual server or the decorator in between. Now we will look at one example of a behavioral pattern, which is template method. So this is again a familiar example where you have a class called shape, and now you want, when you want to implement move operation on shapes, it can be implemented as draw existing shape with color 0, that means blank it out, then change the location and then draw the shape again. Now the draw method, this move method has been implemented in the superclass, but the draw method has to be implemented by the actual shapes. So we have an implementation of move which is in terms of abstract methods which are not implemented in the shape. Now the method move is called template method, whereas method draw is called hook method in this pattern. So this is a very generic requirement which occurs in different applications where you must be able to implement such template methods. So this is one behavioral pattern, and this is its abstract description. So you have the template method which is implemented in terms of a primitive method, and the primitive method is what is implemented in concrete classes. Now we will quickly look at another pattern called strategy pattern. You should be able to use different algorithms at different times, different strategies at different times. For example, a document is composed of text, and various line breaking algorithms can be used in formatting the document before printing. You could have simple compose, determine line breaks, one line at a time, or you could consider lines in an entire paragraph, or each row could have fixed number of letters, which is array type of composition. So these different strategies you can use for justifying your text document, and this is your solution. So you have a document and you have two subclasses. You have various subclasses of your compositor. The document contains the compositor, and the compose is implemented in different subclasses. So this is your strategy pattern. So you have many strategies, concrete strategy 1, 2, 3, etc. All of them implement the algorithms differently. So this is your strategy pattern. And finally we will look at these references to this lecture. The first reference is Eric Gama, Helm Johnson, Lycidas, Design Patterns, Addison Wesley book, and you have another book called by Wolfgang Free, and there is a nice reading available. It's called Pattern Handbook by Linda Rising. There are many papers also available on this subject, so you should go through all this material in order to get more explanation on the slides that I have described. Thank you.